Hi there, this is mg5004 de5418. This is the second of the videos that I am remaking, this time with sound. This is topic 4, class 2. We're looking at logarithmic functions. Logs are just powers of special base numbers. And the base numbers that we usually use are either 10 or E. Now, we learned about E in the previous class. If the base is 10, we talk about common logs. And common logs would be the blue arrow on your calculator. And then we can talk about logs to the base E, and we talk about them as being natural logs. That's, remember, where E is approximately equal to 2.72. And we write these as Ln. Now that's an L, right? This is an L. It's the, whatever letter of the alphabet, that's an L. Ln. And that is the Ln button on your calculator there. Now if you forget, have a look at the little number that's above the Ln. That's e to the x. And if you look at the little thing that's above the log, it's 10. So that's how you remember which is the base that they're talking about. Now we know in maths that already things are opposite. We've got plus and minus, we've got times and divide, we've got something to a power, and then the equivalent root. So we know things go in pairs, and logs and indices are the same kind of thing. And in fact, you've used logs, even though you might not have used the actual word. We already know that 2 to the power of 4 is equal to 16. So what if we went backwards? Suppose we have 2 to the power of x equals 16. Now, we know from what I've just written that 2 to the 4 equals 16, so x is equal to 4. Now, what mathematicians do is they say, well, this is a very special relationship, and this special relationship is called logarithm or logarithmic relationship. And what they say is that if 2 to the 4 equals 16, then log to the base 2 of 16 equals 4. Logs ask us a question. They actually ask us a question. So if I was to write it like this, if I was to write this, so if I was to write logarithm to the base 2 of 32 is something, what I'm saying, what I'm telling you that this notation means is what power of 2 is 32. If that notation means this is a question, then we can answer the question. The answer is 5. And it's 5 because 32 equals 2 to the power of 5. So we know all that. Similarly, we could write the logarithm base 4 of 16 is equal to something. What that says, or what that asks, is what power of 4 is 16, and we know the answer is 2. And we could complete the statement saying it's true because 16 equals 4 to the power of 2. That's all logs are. They ask you a question. What power of that base is the number? Logarithm to base 5 of a 25th is something. we know that it's going to be -2, because what we do know is that 1 over 25 equals 5 to the power of -2. So log to the base 5 of 1 over 25 is -2. What about logarithm to the base 7 of √7? The answer is this must equal 1/2, because the corresponding statement says √7 equals 7 to the power of 1/2. What power of 7 is √7? And the answer is 1/2. Some people like to remember a colourful little picture there. 2 to the power of 3 equals 8. So log to the base 2 of 8 is 3. If you just remember it as a question, you'll be fine. What power of 2 is 8? The answer is 3. And there's the official version there. That's fine. Okay, let's finish these statements here. Log to the base 3 of 9 is 2, and that is true because 9 equals 3 to the power of 2. That is the same as that. Log to the base 4 of 2 is 1/2. That's true because 2 equals 4 to the power of 1/2. So it says what power of 4 is 2, and the answer is 1/2. 1,000 is 10 to the power of 3, so log to the base 10 of 1,000 must be 3. What power of 10 is 1,000? The answer is 3. Similarly, 0.001 is equal to 10 to the -3, so log to the base 10 of 0.001 equals -3. Another example, if I said log to the base 5 of 625, that says what power of 5 is 625, and the answer is 4. And we know that's true because 625 equals 5 to the power of 4. Some people like to remember what goes where with using diagrams, and it doesn't matter how you remember it, whether you remember it by colour or by question or by this diagram here, but it's the same thing. It's asking you what power of A is n. What power of A is n? N is a to the x, so the power must be x. The left-hand side is the index form. The right-hand side is the logarithmic form. Just as we've done before, we can draw all these, but now you will see, because you know, that if we draw y equals e to the x and y equals natural log of x, look, they are mirror images of each other in a mirror line that's on the line y equals x. So if they are reflections in the line y equals x, then they must be inverses of each other. So y equals e to the x is the inverse operation of taking the natural log. Similarly, y equals 10 to the x is the inverse operation of y equals log to the base 10. It shouldn't be any surprise to you that the rules for logs are the same as the rules for powers. So to multiply the log of two numbers, we add the logs. To divide, subtract, and for taking the log of something to a power, the power comes down to the front. Let's figure out how to change base. Now we know that 2 to the power of log 2 to the x is x. If we take the natural log of each side of this, then we've got natural log of 2 log to the base 2 of x equals natural log of x. Let's put it up here. Now, if we use our rules of logs, we can bring that power down to the front. So now we have log to the base 2 of x times natural log of 2 equals natural log of x. And if we divide both sides by natural log of 2, now we have an expression for log to the base 2 of x. It's the natural log of x divided by the natural log of 2. And this would have been true if we'd used logs to the base 2 as well. Let's have a look at this one. Log to the base 3 of 40. Now you can't look that up on your calculator. I don't know what power of 3 40 is, but we can use the rule here that says, okay, let's take log of 40, and it doesn't matter what log you take, and divide it by the same log of 3. And you'd need to work that out on your calculator. Now you can have log of 40 divided by log of 3, and the answer is about 3.58. You need to be able to manipulate logs as well. Let's have a look at 2 log x over y plus 3 log y over x. So what have we got there? We've got, take the power of 2 up, so we've got log of x over y to the power of 2. Now we've got, we can do it all in one go. We've got addition, so that means we're going to be multiplying, and the 3 meant it was a power of 3. Now it's just a little bit of algebra there, and we can work out that all we've got left is y over x, like that. So you need to be able to do those manipulations. On this graph we've got at the top, we've got y equals log to the base e of x, and y equals log to the base 10 of x. Have a look at that. The smaller the base, the higher the curve. E, remember, is approximately equal to 2.7ish, so it's smaller than 10, so it's a higher curve. And remember that when y is equal to 0, the natural log of x is 0, so x must be equal to 1, which is why both of those are crossing there. Just the working for the second one, when y equals 0, log x equals 0, so x equals 1. This is the whole point of learning about logs, so that we can use logs to solve equations. So we've got a situation there, and we have that theta 2 equals theta 1 times 1 minus e to the negative t over some constant. Okay, let's work our way through it. A lot of this we can do without even thinking about logs. So let's divide both sides by theta over 2. Sorry, theta over 1. And then we will take 1 away from each side, and we'll reverse the negative sign. Now, if I'm going to take the natural log of each side, then taking it of the left-hand side, and carry on here. Now we can use the rules of powers to bring down that negative t over the constant. So now we have natural log of 1 minus theta 2 over theta 1 equals negative t over the constant times the natural log of e. And the natural log of e, and this is what makes this method really great, is that the natural log of e is 1. So now we've got natural log of 1 minus theta 2 over theta 1 equals negative t over the constant. And doing a little bit of algebra then, t is equal to negative times the constant, natural log of 1 minus theta 2 over theta 1. Now we've done all of that without actual reference to the question, but it does say that theta 2 is half theta 1. So in actual fact, theta 2 over theta 1 is a half. And then we can merely put that into the brackets to find that t, now we were told what the constant was. The constant was equal to 60, so it would be negative 60 times natural log of, now if theta 2 over theta 1 is a half, 1 minus a half is obviously a half, so we can work out t. Now just think it's a time. It tells us what units, it tells us that it's seconds, so that would be seconds. A simpler one next. If there's no e in the equation, then you can use either logs or natural logs. Let's just use logs. The answer will be the same regardless. So if we take the log of each side and bring the power out to the front, then x is equal to log 7 over log 2, which is a calculator job, roughly 2.8. If we have got e in it though, then we need to use natural logs, because as before what we get is we find that we've got the natural log of e, and the natural log of e is 1, so the whole thing's gone. But first we've got to get rid of the 2. So the first step would be to say that e to the power of x plus 2 is equal to 5 over 2. Now we can take the natural log of each side and we know now that if we bring the x plus 2 down to the front and we're left with x plus 2 times natural log of e is 1. So we're left with x plus 2 equals natural log of 5 over 2. So x is equal to natural log of 5 over 2 minus 2. And again, you calculate a job like that. It doesn't have a unit, so that's fine. Something like log of x equals 1.4. Oops, that's an x, not a slip. So raising it to the power of 10, 10 to the power of log of x equals 10 to the power of 1.4. And we do the same thing, bring down the log of x, etc., etc. Then we get that x, again, you have to use your calculator, x is equal to 25.12. Some questions there to do on your own. The answers are what's written in the brackets. A different kind of problem to solve is one where it's purely algebraic, and let's just start using the rules of logs. So we'd bring the 2 down to the front. 2 natural log times x minus 2 equals natural log x minus 2 minus natural log x plus 3 plus 1.6. Now let's take, we've got 2 natural log x minus 2's on one side and 1 on the other, so let's take that away. And let's add the natural log of x plus 3 onto the other side. And our left-hand side now is a multiplication to be done. If we raise each side to the power of e, our natural logs cancel, so our left-hand side is x minus 2 times x plus 3. A equals e to the 1.6. Now I'm going to take that up to the left-hand side. And look at that, I've nearly got a quadratic. So if you expand out the brackets, you get x squared plus x minus 6 minus e to the 1.6. And it's a quadratic. You've got an x squared term, you've got an x term, and you've got a constant term. So using the quadratic formula, x is equal to 2.847 or negative 3.236. Now just stop there for a moment and look at your answer. If x is equal to negative 3.236, then by the time we put it into this bracket here, we have a problem because you can't take the log of a negative number. So we have to say, well, we've got to discard that answer, and the only answer we've got is x equals 2.847. Now, sometimes we get some crazy graphs. Suppose we're looking at y equals x to the power of 6. If we tried to do that in the normal way, and we had equally spaced x values, so 1, 2, 3, 4, 5, 6, 7, 8. By the time we got up to 10, y is equal to 10 to the power of 6, which means we're not even on the same page. But if we take the log of the y values and plot x against those, then the graph becomes much more reasonable. The y values are compressed a lot, and we're able to then fit it all onto the same page. What we've done here is we've graphed a linear thing, which is the x, against a log thing on the y-axis. So we have a log linear graph. Similarly, if we wanted to graph y equals 7 to the power of x, we'd have the same problem. So if our x values went up in a linear fashion, which they do, scaling would be really awkward. So in this case, if we plot the log of y against x, we get a straight line. This is one of the things about logs, is that they can turn something really quite nasty into linear things. Suppose again we have the graph of y equals x to the power of 7. If this time we plotted the log of x against the log of y, then we're using a log graph, and we get a straight line. And this straight line then is much easier if we want to take, say, if we want to find when x, I don't know, about a half, and there. So log is often useful as well. So we've taken the log of x to give us this column, we've taken the log of y to give us the right-hand column. Let's have a look at this in terms of working out what the equation might be. Now this graph has a gradient of, what have we got, negative 18 over negative 6. So it's got a gradient of 3. So it's log against log, and just knowing what we know about ordinary lines, that would tell us that the log of y was equal to 3 times log x, or that log of y equals log of x cubed. Or if we undid that, we could just say y equals x cubed. But that's clearly not a straight line, but when you take the log of each side, then it becomes a straight line, and it's easier for predicting and interpolating. We can use special graph paper to make this easier. We can either use log linear paper or log. Now the one that we've got here on the slide is log linear. So it has linear, it just goes up 1, 2, 3, 4, 5, 6 on the bottom, but it goes up in logs on the top. And it's what are called two-cycle. See, it says it's two-cycle log linear paper. That's because we're going from 1 at the bottom to 10 to the power of 2. If we were going from 10 to the negative 2 to 10 to the power of 3, then we'd say that was 5-cycle paper. Let's have a look at the information that's given to us here. Now it's not quite clear, but D is the point 1293.19. So let's find the gradient of this line. So it will be log of 93.19. Let's make the comparison with point C. So minus log of 14.85 divided by, now D has the point 12 and C has the x value as 5, so it's approximately equal to 0.1139. So that is the gradient, but what we know is we're thinking that it might be something like, like that. So this tells us that log y is equal to log a plus x log b. Now from here, this will tell us that log b must have been the gradient. So if the gradient is 0.113, then log b must have been the gradient. So that means we can find b as being, take everything to the power of 10, 10 to the power of 0.1139. Now, back over here again, we can see that log of a must be the vertical, I won't call it the y, the vertical intercept. And we can just read that off the graph, that log a equals log 4. So a is equal to 4. So what we've got, this relationship here, is given as y is equal to, now we didn't quite finish off here, 10 to the power of 0.1139 is approximately equal to 1.3. So now our a value is 4, b is 1.3 approximately to the power of x, and that's the equation of a line that's represented here on this log linear paper. In this example, we think that the curve is, now what we're thinking is we've got some data from an experiment and we think it's related y equals ax to the power of n, and we've plotted the data on log paper and this is what we get. Now it's just nice because they all go through points, but it won't always, but near enough. So log y is equal to log a plus n log x. Now, if we're going to use log paper, then we can use capital Y is equal to log y, and capital X is equal to log x, just to make it a bit easier. So y equals log a plus nx. So log a is the vertical intercept, and n is the slope. Now in this particular example we need 3 cycles, so it's going from 1 through to 10 to the power of 3, and we're looking at log. Let's look at the points B, C to find the gradient. The gradient is going to be equal to the log of, let me see, about 255 minus the log of 31 at B divided by, what is it at C, dropping that down at 7, or log of 7 this time, because we're log, and dropping down from 31 we get 3, so log of 3. So we can work out the gradient is approximately 2.5. A is clearly the vertical intercept, so that means that log of little a equals log of 2, so a is equal to 2. So we can rewrite our equation as y equals 2 x to the power of 2.5. So that's going right back to, I've skipped a couple of steps, but I can put it in there. That shouldn't be the capital Y, that should just be a little y. Y is equal to 2x to the power of 2.5.